Today we're just reviewing some things that we already know. We're almost done with Unit 1. We're almost done reviewing things we know. But these are things that are crucial for the rest of the year. So today's topic is domains and range of functions. Just the basic review. And today you can say you're successful if you can determine the domain and range of a graph. And then you can give me the domain of a radical function. Okay, so we're going to start off with just some reminders for interval notation, because I will be asking you to write your solutions in interval notation. So let's review interval notation. Let me help you plan out your note section of this note page. We are going to be putting the reminder for how to do interval notations, 4 definitions, and 3 little pictures. So maybe don't write like a kindergartner. Okay, fit it all in. All right, so we're going to start with interval notation. Interval notation, just to recall, excuse me, how you write those solutions. Interval notation is usually when you have a set of answers that's a fairly large set of answers. Not always, but usually. If we have a set, like, say, for example, we have from A to B, and I use parentheses, I'm indicating that this is an open interval. Okay, it's open, or it's non-inclusive. So if I were to graph that on a graph, and I put A here and I put B here, I would put open circles on A and B, and I just collect up all the space in between. And I'm just trying to get as close as I can possibly get to A and as close as I can possibly get to B, basically just approach them without including them. So that's an open interval or a non-inclusive interval. The other one is a closed interval. Okay, this is what we would call a closed interval or an inclusive interval. It is a bit more finite. Actually, it's measurable. This one over here, the open one's not measurable, because can I get closer and closer and closer to A and never reach A? I could do that for infinity, get closer and closer and closer to A and never reach that. But when I have a closed one, and I put A there and I put B there, and that should have been a closed circle, not a B, there's the B. That's a finite set. When I can actually include A and B, it's just a small set, or maybe it's a large set, but I can include it. Things to remember on infinity, we're always approaching. Infinities are always opened intervals. And then, of course, you can have like a mixed interval that's open on one side and closed on the other. So remember that there are different versions available for interval notation. Okay, next, let's review what a domain and what a range are. So a domain, when we're talking about functions, which is what we started with yesterday, the domain, by the way, that's a noun. It's a thing. The domain is the set, meaning there's more than one typically, of, that's not an A, there we go, A, of all x's. The domain is the set of all x's. So if I were to have a graph, I would be talking about how far does the graph stretch on the x-axis. So this is a left to right measurement. And you always start on the left and you stop on the right, and that's a domain. That's your set of your x's, all your domains. Okay, your range, which is also a thing, it's a noun, is what? It's the set of all y's. So when I measure that, the y-axis, how far does my graph span across the y-axis? I'm measuring from bottom to top. I'm measuring from bottom to top. Okay, so just a reminder of what are we looking for in your domain. It's all of the x's in the answer. What are you looking for in the range? It's all of the y's that are part of your solution. Okay, so there's those terms. And then I have 2 more vocabulary terms, and then I want to do a picture. I'll probably go ahead and do my picture over here in the left-hand side. All right, so my vocabulary term I want to talk about next is a function. Okay, another noun. Function is a thing. Do you guys remember what a function is? Well, you can graph them, but we can also graph things that are not functions. So let's be specific about a function. A function is a relation or a relationship between x's and y's. Okay, it's a relation where each x has exactly one y. And x cannot have two different y's. So if I were to draw a graph of that, of something that maybe was a function, let's see, I'll grab a red pen here. I'll graph a absolute value function, okay? How can I tell by looking at that that that's a function? What test do I use, Isaac? The vertical line test, where if I were to take a vertical line like so, and then I were to drag it across my graph, I would only ever touch the red graph in one spot at a time. That makes that a function because each x has exactly one y. So we could say importantly that it'll pass the vertical line test. That's a really great and quick way to determine if a graph is a function or not. Okay, so there's your function. And then I have one specialized function that I'd like to introduce that I don't think we talked much about in math analysis. We probably should have, but we didn't. And that's the one-to-one function. And I'm in another color, but that's okay because I'm in another definition here. A one-to-one function is a function, which means that it fits the definition of a function. It's a function, okay, where each x has exactly one y and each y has exactly, that's a y and an L, one x. Okay, so there's a one-to-one relationship. If this one is partnered with that two, then that two is partnered with that one, and that's it. So they are a pair, they are a relationship, and they can't be in a relationship with any other numbers. Okay, so this is what we call a one-to-one function. So if I were to draw a picture of a one-to-one function, I could maybe draw a cubic function that goes like that. Okay, so we know this is a regular function, right? Because it passes the vertical line test. Look, passes it? Yes? What other test do you think it's going to pass? The horizontal line test. So if I grab a horizontal line and I cruise across this graph from top to bottom, notice I never touch that graph in more than one spot at a time. So a one-to-one function passes the vertical line test and the horizontal line test. Okay, so that's important to note. So we'll be talking a little bit about one-to-one functions a little bit later in Unit 2. Okay, so let's do a couple little pictures over here in the left hand unless you still have room. So I'm going to do 3 different sets of relationships, and I'm going to map one number onto another. Actually, I'm not even going to use numbers. I'm going to use shapes. So these are my set of x's, and these are my set of y's, and they have a relationship. In the x's, we have a square, and a circle, and a triangle. And over here in my y's, we have a star, and a diamond. And what's another really small, easy one to draw? Oh, that's too much. How about a rectangle? Okay. I guess I could have done a trapezoid, but that's okay. Here we go. So this is my set of X's and this is my set of Y. What I'd like you to do is I'd like you to draw 3 sets of the same picture in your notes. Unless you just think you can watch it and remember it, which is fine. I wonder if I could copy paste. I bet I could. Just take a picture and paste it. Star, diamond, rectangle. Yeah, I could redraw it faster than I can take a picture of it. Okay, here we go. That is a terrible triangle. There we go. Okay, so X's and Y's. All right, so here's what I want to do. I want you to tell me, I'm going to make some relationships between these X's and Y's, and I want you to tell me what kind of relationship it is. Is it a function, a one-to-one function, or it's not a function, it's a relation? What is it? Why is it not a function? Each X has one Y. How many Y's does this X have? 1. How many Y's does this X have? How many Y's does this X have? This is a function. It's a function. Star doesn't have a relationship, but that's okay. It's okay for a Y to have 2 X's in a function. Okay? It's okay. Let's try this one. What's that? Is that a function? No, this X has how many Y's? 3. In a function, an X has to have exactly 1 Y, so we just call this a relation. It's not a function. Last one. What kind of function? This is a one-to-one function because each Y has exactly 1 X. Okay, it's a one-to-one. One arrow going to each thing. And there's no double arrows coming off anything. That's a one-to-one function. Okay, so that's just some mapping and some thinking about the definitions of a function versus a one-to-one versus just a relation. Thinking about the relationship between your X's and Y's. All right, so here we go. Which are functions and why? Okay, is this a function? What kind? This is a one-to-one. What's your justification for that? Passes. Okay, so I'm going to be really quick about this. I'm going to say check vertical line test, check horizontal line test, one-to-one. Justified. It passes them both. If I put an X, then it fails. Okay, what's this next one? It's just a function. Justification for why it's just a function. Vertical line test, but fails the horizontal line test. It's a function, just not a one-to-one. And you can see that it's not a one-to-one because it fails that horizontal line test. How about the next one? That's not a function. It has to pass the vertical line test to be a function. That fails the vertical line test. So you know what we call that? That's a relation. It's not a function. They're all relations, by the way. All right. So it fails the vertical line test. So it doesn't even matter that it passes the horizontal line test. It doesn't matter because it's not a function. Okay. Next one. Yep, it's a relation because it fails the vertical line test. Perfect. Next. Just a function. Not a 1-to-1 because it passes the vertical line test but fails the horizontal line test. Last one. Function. Yep. Passes the vertical line test, fails the horizontal line test. Anybody have questions about that? Anybody need to see me, trail a vertical line across any of those graphs, or you're good to go? All right. So we've reviewed all of the vocabulary and we've talked about what a function is versus what it's not. So now what we're going to do is we're going to spend some time. Let me see if I can zoom in a little bit here. Zoom in. There we go. All right, so we're going to look. Here are the problems that are very similar, like the problems that I'm assigning you for homework. This is like number 16, on your homework tonight. P.S. I didn't give you any that paper you picked up today was a review for your test on Thursday. That is not your homework paper. You got your homework paper yesterday. Remember I gave you 2 through 10 even? Today I want you to keep working on that assignment. So you're going to be doing number 16. What this is right here on the paper is number 15. So it's an example. All right, so let's take a look at this function, and I believe I'll do some color coding here. All right, so we have this function graphed here. It's not a 1-to-1, it's just a function. Okay, and it's a piecewise function because it doesn't go to infinity. And I'm asking you to identify what's the domain, and I want a red pen. So I'm going to do my domain in red. So what I'm looking for is I'm looking at how far does this graph stretch along the x-axis. What's the leftmost point and the rightmost point? Do you agree that I go from here to here? That my graph spans the x-axis from here to here, right? Doesn't extend. Nothing over here is graphed. Nothing over there is graphed. And so, -3, which is my x, and my domain is my x's, all the way to +4. And am I including -3? Is this closed? Yeah, that's a closed circle. So I would say from -3, and am I including the 4? Look at your last point. Is it closed? Yes, so I'm going to include that. So my domain, all of the x's in between have been graphed, all of them. That's how you got that solid line going on. So there's your domain. Let's do a range. Okay, so your range is the measure from bottom to top, so lowest to highest point. So would you consider this to be the lowest point right here? Right here? And this to be the highest point right here? So my measure from there to there is the measure of my span along the range. So inclusive on the bottom, closed circle, inclusive on the top, closed circle. So my range from bottom to, okay, so that's a -2, by the way, on my y, and then that's my other y there. From -2 to 2, closed or inclusive. Okay, so watch those closed circles, because if this graph had an open circle right here, that'd be a different story. Because we'd have to do a little jump maybe. We might have a jump function. Okay, let's take a look at this next one. You were asked to find the f of 1. What does that mean? Y equals 1 or x equals 1? Doesn't that usually say f of x? So I'm substituting x with a 1. So I'm going to come over here to where x equals 1. And what do I get out? What's my output? 0. That's right. So if my x is 1, my y is 0, and there's my solution for that. It's not an interval. It's just a value. Okay? So there's that one. So you're going to have to maybe train yourself and be patient with yourself when you're learning these. They're a little bit frustrating. All right, let's go to the next one here. I'm going to go to a black pen. All x's such that f of x equals 1. What does f of x mean? Y equals 1. So I'm going to come over here where y equals 1, right here, and I'm going to find all my x's. So that would be this point right here. Yes? This point right here, and this point right here. All of those have a y equals 1. What are my x's? -1, 1/2, and 2. So my answer here would be -1, 1/2, and 2. And you could just put that in a set notation if you wanted to. If we were writing it in interval notation, we'd just put closed circles. We could also write it -1, union, 1/2, union, 2. But it's okay when it's just this small at a set of values, just to put it in a set notation. Just put it in a set. All right, let's look at this next set. It says all x's such that f of x or y is greater than 1. So that means that I'm looking for all the points. You know what, I'm going to do a little erasing here so that I can show it to you a little more clearly. So I'm looking for all the places on the graph where y is greater than 1. So here's where y is 1. Okay, so I'm looking for all of the parts of the graph that go above that line. Do you see them? Right here and right here, right? And that is too big of a circle, so I'm going to do this. Erase, 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 erase. And let me try it again with, I can't see my pen. I'll just highlight it here. Here, right? That's greater than 1. And there, that's greater than 1. Okay, can I include? Does it say equals 1 or greater than 1? So what x's am I talking about? I'm talking about all of these x's between here and here. Don't you think? Right? Because that's negative a quarter and up 1 point something, and positive a quarter and up 1 point something. So my y is over that. So I would say between -1 and 1/2, open, non-inclusive, because if I include -1, that won't work because y equals exactly 1. Okay? Union, and then where's my other section? On my y-axis from here to there, right? Because it's domain, because I'm looking for x's. So -2 2 non-inclusive all the way to 4 inclusive or non-inclusive? Is this greater than 1? Is this y greater than 1? Yeah, so you know what? Inclusive. Closed. Because that is greater than 1, and that 4 is part of the answer. So a little tricky. You'll have to practice it. We'll see how you do. Okay, last two, don't go to sleep. So that was like number 16 on your homework. This one is like number 18 on your homework, and this one's like number 28 on your homework. Similar, so you can refer to these as you're working on your assignment. All right, so let's take a look at the first one. Now I'm giving you equations instead of graphs, and I'm asking you just for the domain. So you have to be clued into what numbers are restricted from your set of x's or your domain. This is a square root. There are certain numbers, this number right here is called a radicand, that are restricted from being under a square root. What numbers do we not put under a square root? Negatives. So we must have our radicand has to be greater than or equal to 0. 0 or positive numbers are okay for our radicand, but we can't have any negatives. So when we're looking for our domain, we're looking for excluding all of the x's that create a negative radicand. So here's what we do. We just take our radicand, 2x plus 7. We set it greater than or equal to 0, and we solve it. And that'll tell us our domain. So 2x is greater than or equal to -7, or x is greater than or equal to -7/2. Pretty basic if you're just turning your brain on and you're thinking about what am I restricted from putting in underneath the square root, and that's negatives. So I can have zeros, I can have positives. So if I were to graph that, would I be inclusive of the negative 7/2? Look at that equal sign. Are you sure? Yeah, because I can put a 0 in here. And negative 7/2 would create a 0. So I would put a closed circle there. And then if I want greater than, I'm looking for that section of the number line. So my domain in interval notation, which is my preference, would be closed from negative 7/2 to infinity. And there is your solution for your domain. And that one's not too bad, because your radican's just a linear equation, so it's, it's just pretty easy to do. But when we move to 28, you really have to engage your mind a little bit more, because this is a quadratic. If I multiply that, that's x squared plus 8x plus 12. That's quadratic. So it has how many zeros? Look at this. 2 zeros. Okay, so we have to think about this for a second. So you tell me what you remember. If I have these kinds of numbers under a square root, say for example, I have a positive times a positive, is that okay? Yeah, because that's a positive. That's acceptable. Another option that would be acceptable would be a negative times a negative. That would also equal a positive, and that would be okay. Correct? Another option that would be okay is like if I had a 0 times a positive or a negative, that doesn't matter because that would be the square root of 0, and that's okay. Right? I could also have one other option, and that would be a positive or a negative times a 0. That's an acceptable answer. What's not acceptable is to have a negative times a positive, which is the square root of a negative. That is not allowed. Right? And then, of course, the other option would be to switch those and have a positive times a negative. Are you with me? So what we have to do is we have to identify where we'll get a negative times a negative, or we'll get a positive times a positive, or a 0 times a number, or a number times a 0. But exclude anything that will cause a negative here and a positive here, or a positive here and a negative here. We have to exclude it. So let me show you what this graph looks like real quick. Can I erase this? Well, I'm erasing it, so speak louder if you don't want me to erase it. Okay. So let me show you what this graph looks like. It looks like this. Looks something like that. And if I'm looking for the domain, I don't want this space here in the middle, because that's the space that creates a positive and a negative. So how do we attack this problem? Here's what we do. We find both of our zeros, because if this is a negative 6, right? And this is a negative 6, is that okay? 0 times negative 4 is 0. Or I could pick a negative 2, don't you think? Because 0 times 4 is also 0, and that's okay. But how do I figure out where I get positive and positive and negative and negative? I use my zeros to help me determine that. So here we go. We're going to get our zeros. So x plus 6 has to be greater than or equal to 0 pretty much. But we'll go ahead and just say equals 0, and x plus 2 equals 0. So we get our two zeros. X equals negative 6, and x equals negative 2. So a negative 6 or a negative 2 will produce a 0 under our square root. And I'm going to graph them on a number line, but I am going to make a sign chart, people. So I'm going to stack my two binomials, x plus 6 and x plus 2 over here. And I'm going to start developing some kind of visual tool to help me determine when I have negatives and when I have positives. So here's 1 0. Here's my other 0. This is my number line down here. And I just want you to imagine, here's 0. So what does x have to do to be 0? What does x have to be? A negative 6. So that's a shifting this 0 left 6 spaces. All right. And what's my 0 here? Negative 2. Okay. So what I just did is I took my number line and I created 3 sections on the number line. Let's plug a number in that's less than negative 6. Like, for example, negative 7. What will I get if I plug in negative 7 into x plus 6? Negative 1. What will I get if I plug in negative 7 into x plus 2? All right, that's negative and negative. All right, let's do this next section. Let's say I plug in a negative 4. What do I get? Positive 2. And if I plug in a -4, interesting that the negatives are to the left of the zeros. Let's plug in 0. 0 plus 6 is +6. 0 plus 2 is, again, interesting that to the right of my zeros, I get positives. What? That's just shouldn't happen. Okay, so let's go back now and imagine that we're plugging in two negatives here. So negative times negative is positive. So you multiply those two things. I like that. I can put a positive under here. I like that. How about this situation? That's a negative. I don't like that. That is not part of my solution. And then here, positive times positive is positive. I like that. So this is just a tool to help me see my solutions. And do I include my zeros? Yes, I do include my zeros. So my solution is over here, positive answers, and over here, positive answers. So my domain is from -infinity to -6 closed or inclusive in union with -2 all the way to infinity. That's a lot of x's that are possible, right? It's a very small section of the number line that's being restricted. Okay, so that's like number 28. Do you have any questions?